All right, let's dive into this paper. Physics of Language Models. Part 3.3, Knowledge Capacity Scaling Laws.
Okay.
It's by Zeyuan Allen-Zhu and Yuanzhi Li.
Sounds interesting.
It was submitted for internal review at Meta just this past April 2024.
Mm-hmm.
And it really digs into a question that I find fascinating.
Okay.
What's the relationship between a language model's size and how much factual knowledge it can actually store?
Right, so not like its overall smarts, but just straight up facts it can hold.
Exactly, yeah. Think of it like if a language model were a hard drive,
Okay.
how much data could you actually fit on it?
Interesting analogy.
And one of the things that really caught my eye right away is that the paper suggests there might be a limit, a ceiling.
Oh.
They're saying it could be as low as 2 bits of knowledge stored per each parameter in the model.
Huh. Even with all the tricks we have now, like quantization.
Yeah, even with intake quantization, they're still seeing that limit pop up.
So even making the models more memory efficient, we might be bumping into a fundamental wall.
Right, that's what they seem to be suggesting.
Fascinating. But before we get too deep, maybe we should define what we even mean by knowledge in this context.
Good point.
So in this paper, they're really focused on factual tuples, like little snippets of information extracted from text.
Okay, so like simple statements.
Yeah, exactly. Think of it like Earth, shape, sphere, or water, boiling point, 100 degrees Celsius.
So we're not talking about complex reasoning or anything, just basic factual associations.
Right. It's all about how well a model can store those little nuggets and then actually use them later on.
Makes sense. So to really test this out, they needed a good data set, something they could control and scale up.
Right. You need something reliable to do this kind of research.
And that's where BioD comes in. It's a synthetic data set they created.
Synthetic, so it's artificial.
Yeah, but it's cleverly designed. It's all about biographical information, and they can tweak different parameters.
Okay, I'm intrigued.
So they can adjust things like how long the names are, how many attributes each person has.
So like age, occupation, birthplace, that sort of thing.
Exactly. And they can even control the variety of values for those attributes.
Clever. So they can really isolate the effect of just the model size?
That's the idea. Keep everything else constant, see how much knowledge the model can hold as it gets bigger.
I'm starting to see where this is going.
And the results were surprisingly consistent.
Oh.
No matter how they configured BioZ, no matter what size model they used, they kept hitting that 2-bit limit.
Wow, so it wasn't just a fluke.
Nope. And it wasn't from lack of training either.
They really put these models through their paces then.
Oh yeah, they trained them extensively at like 1,000 exposures to each piece of knowledge.
And still, 2 bits per parameter.
Stubbornly consistent.
Makes you wonder, maybe it's not just about training, but something more fundamental about how these models work.
That's a good question to consider.
Yeah, what about the architecture of the model itself? Does that play a role?
That's what they looked at next. They compared GPT-2, LLaMA, and Mistral.
3 very different architectures.
And that's where things got really interesting.
Okay, I'm all ears.
They found that GPT-2, even though it's older and simpler,
Simpler, how so?
well, it doesn't have all the bells and whistles of those newer models.
Right, like all those fancy gated MLP layers and LLaMA.
Exactly.
Interesting, so simpler sometimes means better?
At least when it comes to storing pure knowledge, especially when you don't have mountains of training data.
I wouldn't have guessed that.
They actually think it might be because GPT-2 is just more stable, easier to train.
Stable, like it doesn't get thrown off as easily.
Yeah, those gated MLP layers, while powerful in theory,
Can be finicky.
exactly, they need just the right conditions to really shine.
So in this case, simple and steady wins the race.
Seems like it. And get this, they even tried messing with GPT-2's architecture, making the MLP layers smaller, even removing them altogether.
Hold on, isn't everyone saying those MLP layers are key for knowledge storage?
You'd think so, right? But the crazy thing is, it didn't really hurt its capacity ratio that much.
You're kidding. So maybe we've been overemphasizing those MLP layers?
It definitely raises some questions.
Yeah, like are we giving enough credit to those attention layers?
Exactly. Maybe they're doing more heavy lifting than we realize.
This is really making me rethink some things.
Me too. But let's not forget about the data itself.
Right, garbage in, garbage out, as they say.
Exactly. They wanted to see how junk data would affect things.
Junk data? You mean like irrelevant stuff mixed in with the good stuff?
Exactly. And what they found was pretty alarming.
Oh no, what happened?
Even a small amount of junk data could drastically reduce how much useful knowledge the model could store.
Seriously. How much are we talking?
Well, in one case, they had a ratio of 1 part useful data to 7 parts junk.
Ouch. That's a lot of noise.
Yeah, and the knowledge capacity plummeted, like a 20-fold decrease.
Even with lots of training.
Yeah, even with 100 exposures to each good piece of information, it still tanked.
That's scary. So data quality really is king.
No doubt about it. But they didn't stop there. They tried to find a way to fix it.
Okay, how'd they do that?
They came up with a surprisingly simple solution.
Let me guess, more data?
Nope, it's all about tagging, think of it like a label.
A label.
They added a special token to all the useful pieces of information.
So the model knows, hey, this is the good stuff.
Exactly, like a little flag saying, pay attention to this.
Clever. Did it work?
You bet it did. In that same scenario with all the junk data, the capacity drop went from 20-fold down to just 2-fold.
Wow, that's a huge improvement.
Just from adding a simple tag.
Makes you wonder what other tricks are hiding in plain sight.
Right, and it also tells us that these models aren't just mindless sponges.
They can actually learn to be picky eaters.
Exactly. They can learn to focus on the good stuff if we give them the right hints.
I like that analogy.
Me too. So we've seen the impact of the 2-bit limit, the role of architecture, and now the importance of data quality.
What's next?
Let's talk about ways to make these models more efficient without sacrificing knowledge capacity.
Sounds good to me. Let's get into it.
So they looked at quantization and sparsity, two hot topics in the field.
Quantization, that's all about using fewer bits to represent the numbers, right?
Exactly. And they found that with int8 quantization, using 8 bits per parameter,
Right.
it didn't really hurt the knowledge capacity at all.
So we can save memory without losing knowledge.
It seems that way. But then they tried in 4, using only 4 bits per parameter. Well, that's where the trouble started. The capacity took a nosedive.
So there's a limit to how much we can squeeze those numbers.
Seems like it. Too much squeezing, and you start losing the precious knowledge.
Makes sense. What about sparsity? That's where things get really interesting with mixture of experts. Or MO.
Right. That's where you only activate certain parts of the body depending on the input.
So it's like having a team of specialists, each one good at something specific.
A good analogy. And what we found with Mo is that it was surprisingly good at storing knowledge.
Really? So we can have our cake and eat it too.
Potentially. It suggests that sparsity could be a key to building bigger, more knowledgeable models without breaking the bank computationally.
That's exciting. So where do we go from here?
Well, we've covered a lot of ground in this first part of our deep dive.
A lot to digest.
But there's still much more to explore. In the next part, we'll dig deeper into the implications of these findings.
And what they might mean for the future of these incredibly powerful models.
Exactly. It's a rapidly evolving field, and the discoveries are just beginning.
Can't wait to dive back in.
Me too.
As we're talking about this, it
Yep.
really strikes me that this 2-bit limit, the fact that it keeps popping up, even with intake quantization,
Right.
it hints at something deeper, something fundamental about these models.
I agree. It's like there's a wall there.
Yeah, and it's not just a limitation of our current techniques.
Like it's baked into the way these models represent information.
Exactly. The paper doesn't say exactly what's causing it,
Right.
but it points to the transformer architecture itself.
And how it encodes information.
Yeah, as potential areas for further research.
So if we want to build models that can hold even more knowledge,
We might need to rethink the whole foundation.
go back to the drawing board.
In a way, yeah. This isn't just about tweaking existing models.
It could lead to a whole new wave of innovation in model architecture.
Absolutely. It's exciting to think about.
Earlier, we were talking about how architectural choices can affect knowledge capacity.
Right, and how simpler can sometimes be better.
Like with GPT-2 outperforming LLaMA and Mistral.
Yeah, especially with limited training data.
Could you talk a bit more about why GPT-2 might have that edge?
Sure. One key factor is probably the stability of the GPT-2 architecture.
Okay.
LLaMA and Mistral, they use those gated MLP layers.
Right, those are supposed to be more efficient, more expressive.
Yeah, in theory, but they can also be much harder to train effectively.
Especially when you don't have a ton of data.
Exactly. They're a bit more sensitive to the initial setup, the hyperparameters, all that.
Whereas GPT-2, even though it's simpler,
It's known for being robust, easier to get good results with.
so in this case, slow and steady wins the race.
It seemed that way. And there's another interesting thing about GPT-2.
What's that?
They found that shrinking the MLP layers, or even removing them entirely.
Didn't really hurt its capacity?
Yeah, isn't that wild?
It goes against everything we thought we knew about MLPs and knowledge.
Right. Everyone says they're essential for storing information.
Makes you wonder if we've been giving them too much credit.
And not enough to the attention layers.
Maybe they're the real heroes of knowledge storage.
That's a great question for future research.
Definitely. Okay, let's shift gears back to data quality for a moment.
Right, the junk data problem.
As we saw, even a little bit can really mess things up.
Yeah, it's like trying to learn from a textbook full of typos.
Exactly. But the researchers came up with a really clever way to deal with it.
Oh, tell me more.
Remember that special token they added to the good data?
Like a quality label.
Exactly. And it worked so well.
It's amazing what a simple trick can do.
It shows that these models aren't just passively absorbing everything,
They can actually learn to prioritize, to focus on what's important.
like training them to be discerning readers.
Exactly. And that has big implications for how we approach data preparation.
Not just quantity, but quality and structure.
We need to think about how to present the information in a way that the model can easily digest.
Okay, let's move on to efficiency now. We talked about quantization,
Right, squeezing those numbers.
and they found that int 8 worked well, but int 4 was a step too far.
Too much squeezing and you lose the juice.
Exactly. So there's a trade-off there. Now, what about sparsity, specifically Mo?
Mixture of experts, my favorite.
You're a fan.
I think it has a lot of potential. It's such an elegant approach.
And the research seems to back that up,
They found Mo is very efficient at storing knowledge
which suggests it could be key for building bigger, more knowledgeable models.
without needing a supercomputer to run them.
Exactly. So Mo might be the answer to balancing scale and efficiency.
It's a promising avenue, for sure.
We've covered a lot of ground, but there's one more piece to this puzzle.
What's that?
What do these findings tell us about the future of language models?
That's the big question, isn't it? Where do we go from here?
All right, so let's wrap things up here. Bring it all together. We've talked about this 2-bit limit, right?
Yeah, a pretty stark finding.
And all the different factors that play into it.
Architectures, data quality, efficiency techniques, it's a whole ecosystem.
It really makes you think about the future of these models, how much they can actually know.
We've encountered this apparent limit on knowledge storage.
But we've also seen some clever ways to work around the challenges.
Exactly, like using special tokens to highlight the good data.
And Mo, which seems really promising for scaling things up.
It's a balancing act, pushing those limits while staying efficient.
So where do we stand? Are we about to hit a wall with how much these models can learn?
That's the million-dollar question. It's hard to say for sure.
But the 2-bit limit, even with int 8,
It suggests there's still room to play with.
like we're not maxed out yet.
Right, and as we explore new techniques, new architectures,
Maybe we can push past that limit.
it's possible. Wouldn't that be something?
Imagine models that can hold more knowledge than any human.
It's mind-boggling to think about the implications for science, for everything.
And this research, it's not just about incremental improvements.
It's about understanding the fundamental nature of knowledge itself.
How do we represent it? How do we access it? How do we use it?
These are deep questions, and language models are giving us a new way to explore them.
This has been an amazing deep dive. Really thought-provoking.
I've learned a lot, even just thinking out loud about these ideas.
Me too. It's clear that this field is moving fast. There's so much more to discover.
And who knows what breakthroughs are just around the corner.
That's the exciting part. Thanks for joining me on this journey. It's been a pleasure.
The pleasure was all mine. And to everyone listening, keep exploring, keep asking questions, because the future of knowledge is being written right now.
Couldn't have said it better myself. Until next time, keep those minds curious.